Hello everyone. So in this video we're going to talk about something called head drop, and we're given a question where we're asked to write, explain and test code to calculate friction factor, head drop given flow, and flow given head drop for a pipe segment. Okay, let's talk about what the head drop is. So the head drop is a change in either pressure or altitude for a certain flow. Okay, let's try to express that in terms of equations. So we know that we have our Bernoulli equation, right? Okay, what was the Bernoulli equation? So the Bernoulli equation was the final pressure minus the initial pressure over density plus final velocity squared minus initial velocity squared over 2 plus the acceleration, gravitational acceleration times final height minus the initial height is equal to the negative of the frictional heating, right? Okay, and we also derived another equation in our previous videos that our frictional heating is equal to 4F delta X V squared over diameter squared, right? Okay. I think I wrote something wrong. Yeah. No, it was, okay. So this was 4 times the fanning friction factor times the length of a pipe over diameter times the velocity squared over 2. Yeah, that's what was our frictional heating equation. Okay, we know that this small f here is the fanning friction factor, and fanning friction factor is related to our Reynolds number for a specific case, and we had our Moody diagram to calculate the fanning friction factor from the given Reynolds number, where the Reynolds number was equal to density times the velocity times the diameter over the viscosity. Okay, so we use our Moody diagram to calculate the friction factor for a specific Reynolds number, right? But in this question, we're going to use something called the Churchill equation, which calculates the fanning friction factor depending on for any given Reynolds number. So this equation on the left side, represents the Churchill equation. Which I got from the internet, and we're going to use that Churchill equation in our code to calculate the fanning friction factor for any given Reynolds number. Okay, what's next? Okay, so now we have our Bernoulli equation, right? And let's say we have a pipe segment and we have a certain flow, and the velocity is not changing. We're going to say that the velocity is not changing, and so that we don't have to take the change in kinetic energy into account, because otherwise our calculation would be very difficult. Okay, so which means this term here is going to go to 0, right? Okay, I'm going to write my Bernoulli equation again. And for the right hand side, I'm going to write down my frictional heating equation, so which is 4 times the fanning friction factor times the length of a pipe over the diameter multiplied by the velocity squared over 2. Okay, what is the next thing we need? Okay, here, for one thing I forgot to mention about the Churchill equation is, for the Churchill equation, we need the diameter of a pipe so that it calculates the friction factor, and also the roughness. It's going to use the roughness to calculate the fanning friction factor. Okay, we are asked to find the head drop, right? So the head drop is a decrease in head. So it can be either a pressure decrease or a decrease in height, which results a certain flow. Okay, to find that, we're going to divide our whole equation to g. So our new equation is going to be g times the density plus z final minus z initial equals -4 times final friction factor over g, length of a pipe over diameter, times the velocity squared over 2. Okay, now we have our equation, and we're in the question where said we have to calculate the head drop given flow, right? So what is our flow? So we know that our flow is the velocity times the cross-sectional area of a pipe, right? So imagine we're given a pipe with a certain length, delta x, and a certain diameter, right? And we also need to know the viscosity, the roughness of our pipe, the viscosity of a fluid and the roughness of our pipe, because we're going to need that in our Churchill equation. And also we're going to need the viscosity to calculate our Reynolds number, right? Okay, so from this equation above for the flow, we can get the velocity, right? So the velocity is going to be equal to 4 times the flow rate over pi times the diameter squared, right? This is our velocity equation. So this thing here, the whole thing, is going to represent our head drop, because head drop is already a negative, right? So we're saying the decrease in head. So we can, if we take a negative of a negative number, it's going to become the positive. So this thing here is going to represent our change in drop, so decrease in drop. And then we need the length, which is going to be provided in the question. We need gravitational acceleration is a constant. We're going to be provided with the diameter. So to calculate the friction factor, we're going to use the Churchill equation from the Reynolds number that's going to be obtained from the viscosity, and we're going to be given the flow rate, right? So from the flow, we can determine the velocity to plug in that equation. So we're going to use a Python code. We're going to have a function where it takes the velocity, the Reynolds number, which we have equation right here. It is the density times the velocity times the diameter over viscosity, right? So we're going to be given the viscosity. Okay, it's going to get the final friction factor from the Churchill equation, and it's going to calculate the head drop. Okay, so our head drop is equal to 4 times the fanning friction factor over g times the delta x, which is the length of a pipe, over the diameter, times the velocity of a flow squared over 2. So our head drop, if we want to express that differently, so if we take a look in our last part of the question, we have to calculate the flow given the head drop, right? So if we want to calculate the head flow from the head drop, we can use the root solver from SciPy integrate in our Python code. So as I said, the head drop is already a decrease in pressure and the height, right? So because of this equation, our head drop is going to be the negative pressure final, or pressure minus pressure initial, g times density, plus change in height. That's going to be our head drop. And in order to calculate the flow, we know that our root solver solves for a particular value of flow that makes some equation equal to 0, right? So let's say we have a given head drop, right? I'm going to say that it is HD. Okay, if I'm going to subtract from that given head drop, my calculated head drop, which is going to be 4F over G x over d times velocity squared 2 should be equal to 0. So if we're going to use the root solver for a particular equation, the root solver will determine a particular value of velocity that makes the whole equation go to 0. Okay, but for that, we know that our velocity, so from this equation, okay, let's say like if we're given the head drop, right? And that's going to be equal to 4 times f. And let's say we have our initial guess for our Reynolds number times the, so that if we have a guess for the Reynolds number, we know the friction factor, right? Let's say like it's equal to 0.01, right? Okay, over d times, okay, it's g times delta x over t times velocity squared over 2, right? So then our velocity is going to be equal to head drop times g times d. Okay, this 2 gets 1, 2, it gets cancelled. Okay, and that's going to become 2 times 0.01 times the delta x, right? And that's going to be our guess. That's going to be our velocity guess because we're guessing our fanning friction factor, right? Okay, then when we're using the SciPy integrate root solver, we need to provide our initial guess for the flow rate for the actual answer, right? Okay, so our flow rate guess is going to become 4 pi d squared over 4, which is the cross-sectional area of a pipe multiplied this velocity. So this whole thing is going to be this velocity. Okay, now we have all the information needed for our Python code. So in the next part of our video, we're gonna work on Python to actually calculate the friction factor from the Churchill equation, to calculate the head drop from our given equation that we calculated, this equation for the head drop, and to calculate the flow given head drop from this equation. So we're going to use the SciPy integrated root solver to find the actual value of flow using our initial guess for the flow. Okay, in this part of the video, we're gonna use our Python to code the computation to calculate the friction factor, head drop given flow, and flow given head drop. Okay, as always, we're gonna start by importing NumPy, as we're gonna be working as numbers, right, and p. And we also need to use a root solver from SciPy optimize. So from scipy.optimize, we're going to import root, and we're going to run it. And then let's say we have water as our fluid, right? So the viscosity mu is going to be equal to 1 times 10 to the power of -3, and our density, which is rho, is going to be equal to 1 times 10 to the power of 3. And we also, the another constant we have is g, which is the gravitational acceleration. So it equals to 9.81 meters per second squared, right? Okay, as we said before, we're going to start by using the Churchill equation to calculate the fanning friction factor for any Reynolds number. Okay, let's say here we have the equation, right, from the internet for the Churchill equation. We have T1 and T2, and we're going to get a function that is going to return this thing, like at the top. Okay, but if you notice, it is not a fanning friction factor, but a Darcy friction factor. So what we need to do with that is we need to multiply it by 2 so that we have a finding friction factor. So we're going to start by defining our function. So let's say we have a function Churchill. Okay, what values it's going to need? It's going to need a Reynolds number and E of D, which is the roughness of a pipe. Okay, let's say we have T1, theta 1, and we need to type this equation. So let's say for the outer we have to the power of 16. Okay, we need to be very careful when we are writing this equation. NP numpy log of, so inside of the log we have 7 over Reynolds number to the power of 0.9 plus 0.29 times E of t. Okay, let's check our equation. So we have the outer parentheses, we have, yep, I think the number of parentheses is correct. Okay, for T2 we're gonna need to write down this equation. Okay, then this is gonna be easier. 16 to the power of what? So 37530 over the Reynolds number to the power of 16. Okay, and it should return as the value, so 2 times the top equation, so 2 times to the power of 1 over 12, right? Okay, and for the inside we have 8 over the Reynolds number okay, I think 0.27. Yep, there was a typo here. Okay, then what do we have? Reynolds number to the power of increased to the power of 12 plus we have 1 over T1 plus T2 to the power of 1.5, right? Okay, let's try to run it. So now we have our Churchill equation, which is gonna give us the value of finding friction factor for a particular Reynolds number. Okay, and we also have to plug in the roughness of our pipe. Okay, the next thing we're gonna do is, let's say we need to calculate the head drop given a flow, right? So we need to have a function that is gonna calculate as the head drop. Okay, let's define a function and call it head drop. Okay, what values is that gonna need? So it's definitely gonna need a flow, and also it's gonna need the length, so let's call it L. And what else? Okay, it is gonna need the diameter of a pipe and the roughness of a pipe, right? Okay, so for the head drop, we need to supply the rate. To the inside, we need to supply the Reynolds number equation. Yes, this one is equal to rho times the velocity times the diameter over mu. And we also, so we don't have our velocity right here, right? So for the velocity, we're gonna say that the velocity is equal to this number. Okay, like this equation from the given flow rate, right? Okay, so that's 2 times Q over NP dot pi multiplied by the diameter squared, right? So that's our velocity. Okay, what else do we need for our to calculate the head drop? So we also need to provide, so we have view, we have the length, we have the, okay, we also have to state that our fanning friction factor in our equation is the Churchill for a particular Reynolds number and the roughness, right? So it's going to get the fanning friction factor using this function on top. Okay, so it's going to return this equation. So it's going to return 4 times F times L times the velocity squared over d times 2. Oops, 2, right? Okay, let's try to run it. Okay, now we have our function to calculate the head drop given the flow rate. Okay, in order to find the equation of in order to find the function for the flow rate, okay, let's say we're gonna start with just a flow equation, and we said like we're gonna be provided with the head drop. Let's say the head drop we're gonna be provided is gonna be just HD, okay? Because as I said in the equation for the flow, we need the given head drop and we need to subtract the calculated head drop from that so that it is going to be equal to 0. So we're going to use the SciPy optimized root solver. Okay, so it's going to be, so we're going to be given the head drop. Okay, what else are we going to be given? So we're going to be given the length, we're going to be given the diameter, and we're going to be given the roughness, right? The same thing with the first equation, but instead of the flow, so it's just the opposite of the first equation. So in the first equation, we were given the flow rate and we were calculating the head drop, but then this one, we're given the head drop and calculating the flow. Okay, so what are the things that we need to plug in? Okay, this thing, we have the Q guess, right? So the flow rate guess, that's going to be equal to np dot pi times the diameter squared over 4, right? Multiplied by the velocity, which is from the guess velocity. So we are saying that our friction factor is going to be equal to 0.01. Okay, so np dot sqrt, so square root of, what are we given? So head drop times g times the diameter over 2 times 0.01 times the length, right? And that's going to be our Q guess. Okay, so this function is going to return us the root of, so for the root solver, we need to provide a function, all right hand side function, so that so inside of the root function, we need to have a function that calculates this. So we're going to have a nested function, and it's going to get this Q guess, so guess flow rate initial guess, and calculate the, so we need to get the answer from the X list, and that's going to be the first element in our list. So as I said, we're going to use the nested loop. So inside of our flow function, we need to provide a right hand side function. So our right hand side function is going to take, okay, what is it going to take? Just the vector, right? It should get a vector. Okay, and our vector is going to be the Q. So the flow rate is going to be our vector, the first element in our vector. Okay, and it should return us this equation. So from the given head drop, we need to subtract the calculated head drop, right? So we can just use this we already have the function to calculate the head drop, so we don't need to plug it in again, like write it down again. Okay, so what this function, so what this right hand side function does is, so it's gonna just provide the number, like it's just gonna give the answer for this equation, right hand side, and the root solver is gonna solve until it gets the right value for our flow, so that it makes this right hand side function equal to 0. Okay, so for our root solver, we're gonna plug in our right hand side equation. And we also need to provide the initial guess, right? And that should be as a list. Okay, let's try to run it and hope we don't have any typos. Oh, cool. Okay, now let's try to check our work. If we did everything correctly, but just given a random numbers. Okay, let's say for our flow rate we have 0.1, and for the length we have 10 meters of a pipe, and for the diameter, let's say it's 0.1 meters, and for the roughness, let's say it's 1 times 10 to the power of negative 6. So the number we are getting here is 9.24 for the flow rate, right? And now let's work backwards to find out if we're gonna get the same head drop if we're gonna get the same flow if we plug in this head drop to our flow equation. So flow is gonna be equal, so for the head drop we're gonna provide 9.2406, let's say, and for the length it is 10 meters, and for the diameter is 0.1, and the roughness is gonna stay the same. Oops. Roughness again 1 times 10 to the power of negative 6. Okay, so we're getting a very close number to 0.1. So which tells us so that we worked correctly to create two functions that calculates the flow when we have the head drop given, and calculates the head drop when we have the flow given. And the Churchill equation is gonna make our work much easier, so that we don't have to use our Moody diagram to calculate the fanning friction factor, so that if we know the Reynolds number, we can just get the fanning friction factor using the Churchill equation. Okay, this was our end of the video. Thanks for your attention.